The title of the presentation is Non-Negative Matrix Factorization for Intrusion Detection Systems applied to IoT traffic. And I am Professor Abderezak Touzene from Computer Science Department, Sultan Qaboos University. So let's move to the content of the presentation. So start briefly about the introduction, problem statement, talking about intrusion detection systems and their evolution. We'll talk about the methodology that we used in this research, experiments, and conclusion references. So as everybody knows, this last decade, there are now a booming of smart devices, millions of connected devices, creating smart city systems, smart transportation, IoT is everywhere. So this will generate huge network traffic. And hackers and attacks on those systems, networks, is really becoming a real problem. So attacks are increasing. The idea is to develop intrusion detection systems able to detect normal traffic, attack traffics from this huge volume of networks. So this is really a big data challenge. So the problem that we are tackling here is really related with traffic generated, which is really at the level of big data, diversity of networks, diversity of devices. We have millions of traffic attacks that are collected for analytics. These traffic attacks nowadays, they are stored in very large datasets. We reach to a level where traditional machine learning based intrusion detection systems, they can be used, but they take a huge time for training and detection. And the idea is designing intrusion detection systems should be really something that be reacting at the real-time level. So that's the idea. We want to develop this new generation of intrusion detection systems. So the big challenge here, the big data challenge is that data, it's a huge volume of data, diversity of data, variety of data, high velocity, because this data is really coming at a high speed. And what to do? So high volume, high variety, high velocity. So these are the three problematics of big data challenge. So to address this in this research is really to try to reduce the dimensionality of the problem. Okay, without losing the information, we try to come up with techniques that are known as dimensionality reduction. And this will help us to simplify the analysis. That's the idea. Intrusion detection systems evolution, starting from the classification where we have this two big class of signature-based, where they can solve the problem as far as the attacks are known and they have like a signature, they can be caught. This limitation here could be when if there is an attack, then those signature based, they don't have the signature and they will be like blind and could not see anything with new or unknown attacks. Anomaly based, there are around 2018. The advantage is really they can cut the attacks because there is rules that can identify a certain normal or abnormal behavior. The problem is that the rules are difficult to implement, and this really can sometimes also the rules can be conflicting, and this is really a big problem. So nowadays, most of the researchers, when it comes to cybersecurity, they use machine learning. And there is a new approach of using machine learning to construct intrusion detection systems. So let's have a look at the category of machine learning algorithms that could be used as base for the intrusion detection systems. So we have decision trees, algorithms, clustering algorithms, trying to going to classifications using a k-mean, or some of them also they can use non-negative matrix factorization. The third category is really looking at the problem by reducing the dimension, and this is where we is our focus. So we use dimensionality reduction. So PCA is one of the algorithms, and also non-negative matrix factorization. So our focus today is on the non-negative matrix factorization. So what is the base of this technique? The problem is that you have a large data set, as I explained. The data set will be represented by the matrix A, where we have n samples as columns and m features as rows. So this matrix is huge. And if we go to do the analytics on this large matrix, it will really take a long time because of the big data. What we do is the following. We try to factorize this matrix, the huge matrix, into smaller matrices. And then we analyze, rather than to do the analytics on the large, we will do it on the small scale. So that's the benefit of the non-negative matrix factorization. So this matrix A will be factorized in two-factor matrices, W, with M features and K base vectors, I will say, product by a matrix H that is known as the coefficient matrix with K by N. The technique that will be used here is an optimization technique. The idea is to decompose this matrix such that we'll get the best approximation in the sense that what we want is to find W and H such that A minus WH will be minimum, meaning this will be the close factorization to A, such that W is positive and H is positive. So that's from where comes the non-negativity. So we want W to be positive because this is where we store the features, and H, the coefficients also should be positive. So that's the argument here. We used an algorithm, so that's in what we call the training phase here, or the learning phase, is really the come up with the factorizations. So training here means we want to find W and H such that A minus WH will be minimum. So we use what we call multiplicative update algorithm that has been developed in 2000. So the data matrix, or if you wish, the sample, the data set, we initialize W and H randomly, and then we start to do the update. So the idea is to first fix W and compute H. And then it's alternated. Once we have the H, from the H, within this specific iteration, we computed the W. So for example, here, we fix H. H here initially is random, and we compute W according to this formula. Okay, so WIG, the elements, will be computed WAG from the previous iteration, AH transpose, so transpose of the matrix. So initially H is randomly selected, of course, positive, divided by this matrix, these elements, WHH transpose for each element. Once we compute all the elements of W, then we fix W. So here you see W is fixed, and we compute the H. So at completing one iteration, we have now new values for W and H. What we can do the test to see if we reach to a specific error that we accept. Otherwise, we do again the loop until we reach to specific error, where we say, for example, here, our W and H are okay. They are close enough to A. And then we can start the detection phase. Once we have completed the training phase, we can start the detection phase. So the idea, or here, how to do the detection, when we have a sample A, okay, so any sample from the data set, for example, any column from data set, like say here, A, in fact, it will be written according to the decomposition, according to the factors like this. So every column of the data set will be written according to W and H with specific, of course, W is the matrix, and H1 here will be the coefficients of this column of the data set, and this will be written this way. Every column or every sample will be written according, it will be a decomposition accordingly. So we have the base here, vectors that we computed, multiplied by the corresponding coefficient. So for the testing here, what we can see here, any element, a new traffic, for example, that is not in the data set that we represent by I here, should be written now according to the decomposition, W multiplied by H dash, where H dash is not known. This is what we want to find out. What will be the coefficients of this sample, new traffic that has not been seen in the data set. We apply this formula to find out, we try to decompose this sample according to W using exactly the same process of minimization. Using this, H dash will be equal to W transpose W inverse, WT multiplied by this new sample I. So this is how we find what will be the decomposition of this new sample, according to the new matrix W. And if you look at the gain here, the thing is that here we are manipulating smaller matrices. If you look, for example, WT, W, all those matrices now, they are reduced in terms of dimension. So this can be done quickly. So that's the benefit of the dimensionality reduction. So there is also one important factor here is, I will come back to it, is the parameter K. The parameter K is in fact very important. You can look at it as a hyperparameter. And this, you can control how much features you need to keep in the your matrix. So for example, you'll see later when I present the results, this parameter is really something that you can control how much you can reduce without losing the information in the large data set. So this is very important. And there is no theoretical studies that will tell, for example, that you should have K within specific things. So that's why you'll see we designed some experiments to find out what will be the best K to reach to our precisions. Okay, so I'm coming back here. Once we have H, so now we have everything. What we need to do to find out which class this new sample will belong to, because this is, at the end of the day, a classification problem. So we want to find out similarity between this new traffic with the previous traffics or previous class of traffics. So we can determine the matching score between the encoding, the new one, the new element, by computing the similarity ratios, comparing here, as you can see, H dash, the new, multiplied by H1, dividing by the norm of the H dash H1. And this ratio H1 will tell me how close I am to the first sample. Okay, S2 will tell me how much I am close to the second sample, and so on and so forth. Okay, because I have n samples. And of course, the highest ratio that we got will be the best or the closest to that specific sample. So we take the SI with the maximum value as the closest encoding. Okay, so when we do the comparison, of course, those samples in the data set, they are labeled. And this will tell us what is the label of the new traffic. So this will help us to have a method to design for multi-class attack. So let's look quickly to the related work here. In fact, we found that there is a study in 2009 presented the first anomaly detection using non-negative. The limitation of these techniques are really using a non-standard data set. So it's very difficult to repeat the experiments to know exactly how accurate the system. And one of the other limitations is really the problem is design, or the technique was designed only to detect only one class. Either they classify normal or abnormal. In our technique, we can say it's normal, abnormal, and we can go further to say, oh, this attack is class 1 attack, class 2 attacks. So this is more accurate, more multi-class IDS. So our methodology to develop the IDS. So first of all, from the data set, we do pre-processing. Then we do the NMF training to compute the WH, test the accuracy, and analyze the results, means the classification. As I mentioned, so we use standard datasets that are used by researchers. One of them is KDD99. This is an international dataset developed in the University of California. It contains a huge 5 million samples as network traffic, 41 features, multi-class labeled attacks. And the second dataset, I will say recent to some extent, developed by, in this paper, Sharafuddin, Canadian Institute of Cybersecurity. Huge, as you can see here, number of samples, and also a high number of features. Okay. So data processing, usually we do like label encoding, because sometimes either some element they are not numbers, then we just give them numbers using Python libraries. And also sometimes some values are very large and we need to do normalization. So we applied min-max normalizations to like our data set. After normalization, we'll have only numbers between 0 and 1. For training and testing, this is the testing phase. For both KDD and CIC datasets, we train the datasets with 30K samples, and we do the testing datasets with 40K samples. 40K. As I mentioned earlier, the difficulty here in the study is when we decompose W and the matrix NWH, what will be the best K? That will be telling us, and it's very important, how much we keep and how much we reduce. If you take a very small K, then the chance that you will remove a lot of information from the data set. Yes, the matrices will be smaller, faster, but you will get less precision. Having a large K is a problem also. Why? Because you keep a lot of information data set, and it's like you are doing the analytics on the whole data set A. So we'll not gain anything out of the factorization. So we did some experiments, as you can see here, and as you can see, there are different values here, and with a different case, and the K equal 10 give us the best results. It give us the highest accuracy. So just keep in mind here. So 41 features. Now by doing the reduction, now we keep only K, 10. So reducing to 10. So this is a huge reduction. But as you can see, we are not doing it blindly. We keep a very good detection accuracy of 98%. So we have the precision and in the same time fast computation. So this is the experiment here. We used on 30K sample KDD data set. K is equal to 10. And then you can see here, iteration after iteration, how the precision is improving. So if we do 100 iteration, so that's will take us like 4 seconds, but the accuracy is not that high. So we need to do more iterations. You see the accuracy is going up. So at 800 iterations, this will take us 31 seconds, and we reach to the precision of 98. If you change the K, it will be a totally different story. Okay, so time will be, for example, if K will be higher, then probably the precision will be higher, but the time also will be higher. So that's the idea that we are talking about here in this research. Now, for the second data set that we use, CIC data set, we did also a similar experiment. First, find out what is the best K by experimentations. And as you can see here, the best K is 13, okay, which give us the highest precision, which is around 90%. So we could not go higher than 90%. Even if you, you see here, even if you increase K, so we really could not improve the detection precision. So better to do fast calculations, keeping the good precision. Same here, as you can see, the precision, if we do 100 iterations, 66 precision, percent accuracy, and as you increase the number of iteration within the factorization, then we reach here 164 seconds, and we reach to our precision of 90%. So in conclusion, we are using the intrusion detection systems based on dimensionality reduction to reduce large problem into smaller sub-problems, easier to handle. So that's the philosophy behind this. We use the multiplicative update technique, the algorithm itself, I just shown before. And the thing is, unlike the previous work, our implementation can detect now multi-class attacks and using standard data sets. So the experimental results here show that we have reached 98% for KDD data sets and 90% precision for CIC data sets. In terms of limitation of our work, so clearly, and you can see it in the CIC data set, that it involves a large computation cost for large data sets. The second problem is slow convergence rate of the technique that we selected, the multiple update. In terms of number iteration, if you want good precision, you need to do more epochs, a high number of iterations, and more iterations you do, and more the cost will be large. So in our future work, we are thinking about extending this NMF IDS to develop a high performance or parallel version that can handle real-time large data sets. So we'll go for parallel processing to do faster computations and take faster decisions in terms of classification. The second future work is looking at the techniques. Are there faster techniques, for example, in terms of convergence, reducing the number of iterations, because the number of iteration has a high impact on the final calculations or the time to do the factorizations. So we are looking at, for example, trying other techniques like hierarchical alternate least square, and also developing our new ideas on how to make these techniques converge faster, because this is very important. The faster convergence, the faster the detection. So these are the references. And thank you very much for listening. If you have any